About references and borrowing. The issue with tuple code in listing 4-5 is that we have to return the string to the calling function so that we can still use the string after the call to calculate length, because the string was moved into calculate length. Instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at that address. That data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for life of that variance. Here is how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking the ownership of the value. Okay, so the ampersand and like the ampersand, it means that it is borrowing instead of taking the ownership. Okay, so I can still use s1 after calling calculate length. First, notice that all the tuple code in the variable declaration and the function return value is gone. Second, note that we pass the ampersand s1 into the calculate length, and in its definition we take ampersand string rather than the string. This ampersand represents references and they allow you to refer to some value without taking ownership. Figure 4-5 depicts this concept. The opposition of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator star. We will see some of the use cases of the dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. So here we are creating a string, then in calculate length we are borrowing that string s1. The ampersand s1 syntax let us create a reference that refers to the value of s1 but does not own it. Because it does not own it, the value it points to will not be dropped when the references stops being used. Likewise, the signature of the function uses ampersand to indicate that the type of parameter s is a reference. Let's add some explanatory annotations. Okay, s is a reference to a string. Here s goes out of scope, but it does not have the ownership of what it refers to. It is not dropped. The scope in the variable s is varied in the same way as a function parameter scope, but the value pointed to by the reference is not dropped when s stops being used, because s doesn't have the ownership. When a function have references as parameter instead of the actual value, we won't need to return the values in order to give back ownership, because we never had ownership. We call the action of creating a reference borrowing uh, as in real life. If a person owns something, you can borrow it from them. When you are done, you can give it back. You don't own it. So what happens if we try to modify something we are borrowing? Spoiler alert, it doesn't work. So if you s ampersand s, okay, some string, okay, this won't work. I think there is a way around this, where by passing ampersand mute, but for now this would give you an error because you can't modify this. Here, just as variables are immutable by default, so are references. We are not allowed to modify something we have a reference to. Mutable references, we can fix the code from listing 4-6 to allow us to modify a borrowed value with just a few small tweaks that use instead a mutable reference. Fun main, let mute s equal to a string colon colon from hello, change ampersand mute s. Okay, so here you can, it does allow you to change the value. Oh, also notice that this should be a mutable. Okay, first we change s to be mute, then we create a mutable reference with ampersand mute s, where we call the change function and update the function signature to accept a mutable reference with some string ampersand mute string. This makes it very clear that the change function will mutate the value it borrows. Mutable references will only have one big restriction. If you have a mutable references to a value, you can have no other references to that value. This code that attempts to create two mutable references to s will fail. Let mute s string colon colon from hello, let r1 and mute s, let r2 and mute s. The error says that this code is invalid because we cannot borrow s as mutable more than once at a time. The first mutable borrow is in r1 and must last until it's used in the println. But between the creation of that mutable reference and its usage, we try to create another mutable reference in r2 that borrows the same data as r1. The restriction preventing multiple mutable reference to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new rustaceans struggle with, but most languages let you mutate whenever you would like to. The benefit of having this restriction is that Rust can prevent data races at compile time, or data race is similar to a race condition and happens when this three behavior occurs. Two or more pointer access the same data at the same time. At least one of the pointer is being used to write the data. There is no mechanism being used to synchronize access to the data. Data races causes undefined behavior and can be difficult to diagnose and fix when you are trying to track them down. Rust prevents this error by refusing to compile code with data races. As always, we can always use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous cases. Let mute as r1 goes out of scope here, so we can make a new reference with no problem. Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. Let mute s equal to string colon colon from hello, let r1 equal to ampersand s, r2 equal to ampersand s, r3 equal to ampersand mute s. Okay, and then we have a println view. We also cannot have a mutable reference while we have an immutable one to the same value. Users of a immutable reference doesn't expect the value to suddenly change out from under them. However, multiple mutable references are allowed because no one who is just reading the data has the ability to affect anyone else reading of the data. Note that a reference scope starts from where it is introduced and continues through the last time that the reference is used. For instance, this code will compile because the last usage of the immutable references. The println occurs before the mutable reference is introduced. Okay, the scope of the immutable reference r1 and r2 end after println whether they are last used, which is before the mutable reference r3 is created. These scopes don't overlap, so this code is allowed. The compiler can tell the reference is no longer being used at this point before the end of the scope. Okay, and let's see, I have something like this, but if I remove this, okay, it does allow me to do that. The scope of immutable references. Okay, even though borrowing errors may be frustrating at times, remember that it's a Rust compiler pointing out a potential bug early at compile time rather than at runtime showing you exactly where the problem is. Then you don't have to track why your data isn't what you thought it was. Dangling references in language with pointer, it's easy to erroneously create a dangling pointer that references a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory in rest. By contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the references to the data does. Let's try to create a dangling reference to see how Rust prevents them with a compile time error. Okay, ampersand string, let string s equal to hello ampersand s reference to nothing. This error message refers to a feature we haven't covered yet, lifetime. We will discuss lifetime in detail, but if you disregard the parts about lifetime, the message does contain the key to why this code is a problem. This function return type contains a borrowed value, but there is no value for it to borrow from. Let's take a closer look at exactly what's happening at each stage of our dangle code. Solution here is to return the string directly. Because s is created inside dangle, when the code of dangle is finished, s will be deallocated, but we try to return a reference to it. This means the reference would be pointing to an invalid string. That's no good. Rust won't let us do this. Solution here is to return this works without any problem. Ownership is moved out and nothing is deallocated. Rules of reference. Let's recap what we have discussed about. At any given time, you can either have one mutable reference or any number of immutable references must always be valid. Next, we will have a look at what kind of reference slices, different kind of reference slices. So yeah, that's it for today's video. Thank you for watching. See you in the next one.